Even the simplest Carnot power cycle problem is still pretty involved, so what I wanted to do was to sketch out how you would approach evaluating the work done, in this case by an ideal gas Carnot power cycle. So let's draw out the PV diagram, and remember, process 2 to 3 is isothermal at a temperature T sub H. You can tell on this diagram that it has to be the higher temperature. Process 4 to 1 must be at T sub C. Okay, and we're told that this is a power cycle in this case, so we know that it goes in order 1, 2, 3, 4, back to 1. Okay, now this has to be a gas power cycle rather than a vapor power cycle, right? You can tell from the shape, because remember, processes 4 to 1 and 2 to 3 would be horizontal lines if it were a vapor power cycle. You also know, since I said it was an ideal gas, you better make sure that you're actually dealing with a gas. You can't apply the ideal gas law to liquids. Okay, so process 1 to 2, using the same numbering that I used in lecture in the previous video, is adiabatic compression to reach temperature T sub H. So it's that path right there. Let's say that I want to compute the work done, again with an ideal gas Carnot power cycle for this process. Okay, well, I would start with conservation of energy, and we know that for process 1 to 2, I'm assuming that we're dealing with a piston or something so that it's a closed system. I have to be a little careful here. You can actually execute Carnot cycles that are not closed systems, but for now, we'll assume it's closed so we don't have all of those m dot terms. Let's further assume that the kinetic and potential effects are unimportant, so that delta Ke equals delta Pe equals 0. That means that we can reduce the left-hand side of this, delta E12, to being just the change in total internal energy, so delta U12. All right. If it's adiabatic, which I said it must be, then that tells us that Q12 is 0, so automatically we know that there's a direct relationship between the change in internal energy and the work done. Okay, I'll rearrange that to solve for the work. And now you could actually stop here, as long as you had some way of determining delta U12. I'm going to go a little bit further because, of course, there's a standard way of calculating the change in internal energy for an ideal gas. So first, let's write out that difference. Let's change delta U12 into U2 minus U1, okay? And let's pull out a factor of the mass and put that minus sign inside the parentheses so I don't forget about it. So W12 becomes the total mass of whatever's in the piston times the quantity little u1 minus little u2, dealing now with the specific internal energies. Let's think about this for a second. Little u1, that has to be the specific internal energy at temperature T sub C. And since we're dealing with an ideal gas, all you need to know to specify that value is its temperature. Likewise, little u2 has to be the specific internal energy at a temperature T sub H. So we can rewrite those without the number subscripts, just as U1 equals U at temperature T sub C, U2 equals U at temperature T sub H. And just to be clear, I'm not multiplying by those temperatures. The temperatures are written there to illustrate the temperature at which the variable U is being evaluated. Okay, this is about as far as we can go. Now you can imagine with an ideal gas problem, if you had information about the specific internal energies, like you would look them up in a table, you would just put those in, put in the total mass, and you'd get the work. You could also imagine having to employ the specific heats to get the difference in U at two different temperatures, but you should already know how to do that, right? Okay, so that's the work expression just for process 1 to 2. I'm going to go through and compute work expressions for all three of the other processes, and then at the end we'll put it all together. So what about process 2 to 3? That's an isothermal expansion at fixed temperature T sub H. I've highlighted the path up there. Let's start with conservation of energy again. Delta U23 equals Q23 minus W23. Well, you might be able to convince yourself that since we're dealing with an ideal gas, and we're at the same temperature for the two different states, 2 and 3, that actually the left-hand side of this is 0, right? Because delta U23 should be 0. You'll basically just be evaluating the internal energy at temperature 2 and temperature 3, but they're the same temperature. That's very helpful if you know the value of Q23, because then you can immediately solve for W23. What I'm going to assume, though, is that we don't know the heat transfer. We don't know Q23. In that case, conservation of energy may not be the way to go. Fortunately, we actually have a way of computing the work directly using the integral of PdV. So let's write that out. W23 must be the integral from V2 to V3 of PdV. Remember, that's how the work is defined. So we can use the ideal gas law to relate P and V. P big V equals MRT, and in this case specifically it's T sub H. I don't know if you noticed this, but everything on the right-hand side of that is constant. If we assume we're dealing with a piston, then M is constant, R is certainly constant for a given gas, and we're dealing with an isothermal process, so T sub H is constant. Guess what? Isothermal ideal gas process is a polytropic process with n equal to 1. That means that PV is constant. Okay, that's great. So we can rearrange and solve for P. P is just MRTH over big V, And now we can insert that into the integral for the work. So W23 becomes the integral of that entire thing over dV. And we know how to solve this integral. We've probably done it a dozen times. So it becomes the constant mRTH times the natural log of V3 over V2. There are a few different forms in which you can rewrite this. One just translates big V to little v, right? They're related by a factor of mass, but if you have that in the numerator and denominator of the argument of the natural log, then you can just cancel out the masses and get that it's mRTH times the natural log of little v3 over little v2. Likewise, you could go back and reapply the ideal gas law if you wanted to write this in terms of like a pressure ratio or something. It depends on what you're given in the problem. Okay, that's W23. Let's move on to process 3-4. Process 3-4 is an adiabatic expansion to reach temperature T sub C. Guess what? We already did energy balance for an adiabatic process, right? We said that it had to be this because the heat transfer had to be 0 since it's adiabatic. So W34 equals minus delta big U34. Pull out a factor of mass just like we did for process 1-2, put the minus sign in the parentheses, and we get a final result that looks very similar to process 1-2, except that it's negative. So W34 is negative W12. That's interesting when we put this all together. Presumably that will be an important detail. Let's just move that up for a second. Likewise, process 4-1, it's isothermal. We already made the argument that an isothermal ideal gas is polytropic with an index of 1. You do the same sort of integral just with different limits, and you should get out that W41 is mRTC now, because we're operating at the cold temperature, times the natural log of little v1 divided by little v4. I'm going to summarize all four of the expressions that we just came up with. So W12 is this, here's W23, 3-4, and 4-1. Our goal now is to evaluate the total work done by the cycle. Well, of course, the total work is just the sum of all four of the works associated with each individual process. Now that you see the expressions next to each other, hopefully you can convince yourself that W12 equals minus W34, so those two cancel. That may actually seem weird when you look over at the PV diagram. It's not obvious that the area under process 1-2 cancels out with the area under process 3-4. There's two reasons for that. One is that generally PV diagrams are not drawn with uniform scales. They're not drawn that carefully. Specifically, I did not draw this one that carefully. It's also the case that the curvature of process 1-2 is not exactly identical to the curvature of 3-4, so you can imagine that kind of fools the eye in computing the areas. Regardless, we just convinced ourselves that the two areas have to be equal. One will be associated with positive work, one with negative, so they cancel out. So all that's left is work from W23 and W41. We put that together, it's just the terms involving the natural logs. And remember, you can go back through if you don't like ratios of specific volumes. You can rewrite those as pressure ratios using the ideal gas law. Likewise, any term you see that involves an MRT out front, you could, of course, rewrite as a PV for that particular temperature, again using the ideal gas law. Two final comments. One, we've computed the total work associated with a power cycle. That means that we've automatically computed the total heat transfer associated with that cycle. Remember, W cycle equals Q cycle. Second point, this was for an ideal gas Carnot power cycle. These results that we've just come up with would not apply to a vapor power cycle that occurs within the vapor dome. For that, you would probably need to use lookup tables or something. At the very least, you could not use the ideal gas law.